Good morning, everyone. So I hope you're excited. Myself and a few co-authors, you can see them at the bottom there, we wrote a paper on how to improve the current state of the art of how we do microbenchmarks. But that brings us to a question. A lot of slides, sorry. What on earth is a Java microbenchmark? So the people that wrote the Java Runtime Environment also wrote what we call the Java Microbenchmark harness. What this is used for is to test specific features or functions within a class and benchmark those functions in the Java Runtime Environment. The reason for this is that the Java Runtime Environment does what they call a, I forgot the name now, but it essentially tries to reach a steady state, where a portion of the code is automatically converted into bytecode. Now, the warm-up phase is our first phase. This is where the Java Runtime Environment doesn't know how to optimize your code yet. It's trying to look at places, see what gets called often, and then the results are all over the place. If you try to test this, you'll see wave functions that go up and down, and it's very unpredictable, and we want reliable results. So then we get to what we call the steady state phase. The steady state phase is the second and final phase, and I'll tell you why I put those in quotes later. And at this point, we assume that the Java Runtime Environment has optimized your code as much as it possibly can. These results are always stable and reliable, and they don't fluctuate with beyond a reasonable bound. Now, this means we have an assumption that we will always have a warm-up phase and always have a steady state phase. We also have an assumption of time, that after a particular amount of time or a particular number of iterations, we then will reach a steady state. But we found, or rather, Luca Trainee and some of his friends tested 584 benchmarks. Now, that might seem little, but these tests took 95 days to fully complete. Just showing you the realm of why we really want to figure out, do these things reach a steady state? Can we reach it faster? Is our assumption wrong? And they found that in only 43% of the cases, we reached a consistent steady state. This means that 57% of the time, we sometimes reach a steady state and sometimes don't, meaning that waiting for steady state is completely useless at the end of the day. They also found that there was a 41% median deviation in the amount of iterations it would take to reach the steady state, meaning that sometimes we'll reach it sooner, sometimes we'll reach it later, and these assumptions that developers make. Because just a bit of background, the current state of the art is some expert developers think up a magic number and say, after 50 seconds, start benchmarking for the steady state, or after 12 seconds, start benchmarking for the steady state. And this is wrong, right, as these people have found. And that got my team and myself thinking, how can we predict this in a different way? How can we take the human error out of the equation? And as you all know, machine learning is always the art. But this comes in the form of two things. The first is static source code features. What if we can look at what your source code looks like and predict, hey, you have this many for loops, this many resource access functions, you have these many parameters and functions. What if this static source code can tell us our possibility to reach a steady state, or even how long it would take to reach a steady state? And the second is the steady state performance. This is from a large, like 50 gigabyte data set that the people that wrote the initial paper gave us. And we use this 50 gigabytes of data to map what we had, the source code features, to the steady state performance. So this, to get the static source code features, we downloaded each library from GitHub with the corresponding version tag, and then we extracted all of the 127 features that ANTLR supports. Now, ANTLR is a library that uses abstract syntax tree parsing. Who knows what that means? There we go. It's a common term in compiler construction. That's how your compiler knows what your code looks like, what functions are in your classes, and different things like that. And we use this library to extract what the class actually looks like. Then we did what we call correlation studies. The first is Pearson's R, which is a measure of linear correlation between two sets of data. Spearman's rho, a measure of the relationship between two variables using a monotonic function, and Kendall's tau, a measure of the ordinal association between two measured quantities. That's a lot of gibberish. What it basically means is we try to map a given x value to a predicted y value. In this case, can the amount of occurrences of a particular feature mean we reach a steady state or don't reach a steady state? Or can the amount of features of a particular class map to the iterations it would take to reach a steady state? And this is the question that the correlation studies answer. And then finally, of course, we do some machine learning with some binary classifiers to try and predict, can we predict that it will always reach a steady state or not? So now some graphs. This is what all of the data scientists love. And this is just a quick overview. I'll go into each of these graphs in more detail in a moment. But just to show you what the correlation study looks like. So you see a lot of things go beyond a center line. That center line is a zero correlation. And that means that the amount of features have absolutely no effect on whether or not you reach a steady state. But the values that go far to the right-hand side, you'll see they have a positive correlation. That means the more of this feature exists, the more chance we have to reach a steady state, or the more it takes, the more time it takes to reach a steady state. Inversely, if it goes into a large negative, that means the less of this feature you have, the better your chances are of having a steady state. So just having a look at the more nitty-gritty, just so you can see some of these features, you can see that in Pearson's, now this is for each type of correlation study, we have separate graphs. So we have the Pearson correlations of different features on the ability to reach a steady state. You'll see that the finally block has about like a 13% positive correlation, and you have something like generic interface method declaration, that's a word, that has a negative 8% correlation. And similarly, we have Kendall, which has about like an 8% positive and 6% negative. And Spearman and Kendall are very similar in their mathematical equations, so it makes sense that their graphs are very similar. Then on the iteration to reach a steady state, and this is where our paper really took an upward scale, where we suddenly have correlations of upwards of 14%, and in cases of Kendall and Spearman, upwards of 17 and even 21% positive correlation. That means we've got something. That means we're actually able to find some things that have a very significant impact on the ability, or in this case, the iterations it would take to reach a steady state. Then we did a lot of machine learning. You'll see a lot of the different methods we used on the left there, changing some of the defaults and just seeing what results we get there. But you'll notice a nearest neighbor right there in the Spearman column has 78.6% accuracy, which is really good. We can actually fairly accurately predict whether or not a particular iteration or particular source code feature would, or given a number of very significant static source code features, we can determine whether or not it would reach a steady state. And just some more information for the data science nerds out there. We've got some precision recall, F1 score, and confusion matrix on the distribution of the classifications. And then this you will not find in the paper itself, but it's just a nice fun thing we did after we wrote the paper. We tried to look at what the TS&E distribution looks like. Now, TS&E distribution tries to find clusters of data. You'll see we have inconsistent steady states in blue and consistent steady states in orange. You can see a lot of overlapping things, but you can also see some shapes. And this gives us a pretty confident conclusion that our data set isn't a linear data set. It isn't a one-to-one. It's more of a three-dimensional data set where you map multiple features and try and find a correlation between multiple features and a single result. This, unfortunately, we didn't have time for it. we came to a few conclusions. The first is that correlations can be found between by mapping a feature to a resulting run. And an even greater correlation can exist for iterations it takes to reach a steady state. And using machine learning models, we have a very, very good indication that machine learning can help us to improve the current state of the art and further improve how we do steady state performance.